seen before, which is helpful, which is good. But where we ended on Friday, I don't want to totally make you guys lose our spot. The unit circle isn't until section 4.2. So some of you were like, we were right there. We were really close. We were really close. But here's what I want you guys to see. Okay? Even though there is this chick named Vihart and she says that tau is better than pi, just for you to be prepared for future maths and how our entire math kind of around the world is based, we need to be using pi, not this great guy called tau. So, to think, okay? I need you to start thinking in fractions. We're going to talk more about this as we get the kinds of fractions I need you to know off the top of your head. But for right now, I need you guys to take this picture really quickly, okay? Take this picture really quickly. We talked about last thing on Friday where pi comes from. Pi comes from the distance around a circle divided by a distance across a circle. Our flexible ruler with units of radiuses, aka radians. For that flexible ruler marked by radiuses, or aka radians, to wrap it, meet halfway or go completely halfway, or meet the straight line through 180 degrees. I would need 3.1415926. That would be the perfect units, aka pi. But 1/6 of pi, 1/4 of pi, 1/3 of pi, 1/2 of pi, 1 whole pi. I need you guys to realize that 1 pi is really a calzone. Good, me too. Or you can call it a taco if you want, but that's kind of lame. Because when I think pie, I think pizza pie. But I need you guys to not think about a full circular pie because that won't make sense. What do I need you to think about? A calzone or a taco. Calzone's more fun. What's a calzone? What is it, Robbie? What? Yeah, kind of. It's a pizza folded in on itself. What size is a normal pizza? What's a calzone? You basically take a pizza and you fold it in half and you squish the edges and you bake it. And it's just like a amazing, like half circle. Ah. Yeah, it's a much better Hot Pocket. Well, depending on where you get the calzone from. But anyway, if you haven't had a calzone, you should try one. Be like, hey, it's pi. I'm doing math homework. Anyway, so pi is only half a circle. So how many calzones would it take to make a full circle? 2, right? What would half of a pi be? Oh, 90 degrees. What would 3/4 of a pi be? Oh, it'd be almost 1 full calzone. 1/3 of it, oh, it'd be right there. And we need to start thinking about pi as a half circle, otherwise we're going to get in some pretty big trouble pretty fast. But once again, that's not the whole point of section 4.1. Introducing radians and what they are, flexible rulers of radiuses, and just introducing the idea of pi being half a circle and not a full circle, etc., was only part of it. We have to finish up the section with some details. So, first of all, coterminal. Coterminal. Angles that share a terminal side. And if you guys know prefixes at all, co, with, or together. Co, with, or together. Co-worker. You work with or together someone else. With or together with someone else. Cohabitate. Living with someone else. Company? No, that's not really a prefix. That doesn't work. What? Co-manager, yeah. Or I was thinking co-president. Like if you're with or together someone else, like say your position is shared, right? If your position is shared. Huh? Oh. Yeah. So co-terminal, with or together, they end at the same place. This is where it gets a little trippy because we could go to somewhere like, hey, working on our pi is calzone is half a circle kind of thing. If this is pi over 4, couldn't we get to this final location by just turning 45 degrees? True? But what's another way that we could end or be with or together the ending of this angle? Couldn't we spin and then end? Now hold on, spin and then end. Question, How many degrees are in between the pi over 4, the first angle that we had, which we could call alpha, and then the second angle that we had that you had to spin to end, or to get to? What's in between them? I heard 90, I heard 180, I heard 2 pi. I have a lot of different answers. What's in between? If I was to do beta minus alpha, what would I get? 360 degrees, and 360 degrees is the exact same thing as 2 pi. You need 2 half circles in order to make a full circle. If I was to subtract beta and alpha, I would get a full circle in between, right? If I was to take that away, it's a full circle. So I would get 2 pi, or I would get 360. What's another way that I could end on that exact same location, but spinning a different direction or a different amount of time? Counterclockwise. Yeah, I could go this way. Alpha, beta. Do you want to do gamma next? That is clockwise. I think counterclockwise is what we were doing the first time. So if you go clockwise to it, alpha would be pi over 4. Has anybody figured out what beta would be? If there's 2 pi between them? I could say that beta is 2 pi plus alpha, right? What would 2 pi plus alpha be, or 2 pi plus pi over 4? Not 4 over 5. 405? Oh, you're thinking about degrees. Oh. We're trying to think in radians. So if we have 1/4 and 2, how many fourths is in 2 whole? 8. So then 8/4 plus 1/4, 9/4. There you go. What would my gamma be? What's the relationship between gamma? Oh, that's so horrible. That's okay. What's the relationship between him and... I think he goes together with him to be one full circle, right? Alpha and gamma would make one full circle. So then how could I think of... Wait, couldn't I do 2 pi minus? But that's going to be a positive number. Hold on. Angles that turn the other direction, aren't those negative numbers? So couldn't I do alpha minus 2 pi? So that'd be pi over 4 minus 2 pi, which would be 1/4 minus 8/4 would be negative 7/4. Now, can some of you do this with degrees? Yes. Do most of your brains work better in degrees? Yes. We'll talk about that in just 1 second. But for right now, we're going to go ahead and say 2 angles are coterminal if and only if the latter angle is equal to the original angle plus or minus multiples of 2 pi n. Because as we realize, you can either add 2 pi or you can subtract 2 pi. And we didn't even get into adding 4 pi and subtracting 4 pi, adding 6 pi and subtracting 6 pi. We can find infinitely many coterminal angles. As long as we're adding and subtracting. Okay, some of you might need to put this expression in words. Multiples of 2 pi. Because n is an integer. N is an integer. And as I learned in church last week, integer comes from the word wholeness. Integer comes from the word wholeness. So if you're integrating something, you're trying to make it complete, you're trying to wholly incorporate it, etc. Interesting, huh? Ooh. Well, it came from my pastor, Brad Zarian. Sounds like something Mr. Carmichael would know too. Integer, wholeness. So whole numbers, like n equals 1 or 2 or 3 or 4. And technically, n could be negative numbers too, but I put the plus or minus to show you guys you can be adding or subtracting. Because some of you wouldn't realize if I just put plus, you can add or subtract. Now, if it helps, and if you're more of a degree person, you could go ahead and you could also say the definition is technically 360n when we're talking about degrees. You could also put that. That's technically true. If we're talking about degrees, you can be adding or subtracting multiples of 360. And that, I think, Adam, is what you were doing. You were adding 45 to 360, right, to get 405. Good. Complementary. You guys remember these ones from before? Angles that are complementary versus angles that are supplementary. Let me do a quick example. Complementary. If I was to do something like pi over 6 is alpha, and pi over 3 is beta. Between pi over 6 and pi over 3? What's true about 30 and 60 degrees? Maybe I'll do it this way. So if I do pi over 6, if I do pi over 3, what would happen if those were two little cutouts and I gave them to you right now and you put them together? What would happen? Pi over 2. Because that would be the exact same thing if I had my little alpha and if I had my little beta. Alpha plus beta equals 1 pi over 6. Hey, isn't pi over 3 really just 2 pi's over 6's? Right? And if I put them together, I end up with 3 pi over 6's, aka pi over 2. Complementary angles are angles that add up to pi over 2. And for my degree thinking people, it is 90 degrees. Good, but remember we're trying to get into radians. And 90 degrees is half a calzone, which is a quarter of a whole circle. Half a calzone. 90 degrees, pi over 2. Now, we do need to be careful with these ones. Okay? These ones, special types of angles. These descriptions are for positive angles. Meaning you can't go past 90 and then add a negative angle. You can't do like 110 and negative 20. That doesn't work. They're positive angles that if you were to put them together, if you were to literally have cutouts and add them to each other, not a negative angle going a different direction, but positive angles. You can also think of absolute value of angles. I don't like that description. That gets too complicated. So positive angles being added up to 90 or to pi over 2. Supplementary. Well, if this one adds up to 90, what's this one going to add up to? So we're going to say add up to 180 in parentheses, but what is that? Oh, that's a half circle, and a half circle, that's a calzone. Pi. Add up to pi. Can someone give me an example? If I was, well, not even an example. Can you finish my example? What if I was to give you, here we go, 2 pi over 3, 2/3 of a calzone. What would be its supplement? Why? What does 2 pi over 3 and 1 pi over 3 add up to be? 3 pi over 3. So alpha plus beta is equal to 2 pi over, oops, I named them wrong. That's okay. Pi over 3 and 2 pi over 3. Three pi over 3 or pi. What I'm trying to remind your brains is, even though we've talked about how 1 pi can be a calzone, remember that calzone can be cut up in all sorts of different pieces. So if that calzone is cut into thirds, that means there are 3 pieces that comprise that calzone. And 2 pieces would be 2/3 of it, and 1 piece would be 1/3 of it. If we were to cut pi into sixths, if we were to cut pi into sixths, there would be 6 different pieces, and I could say, oh, there's 1/6 and 2/6 and 3/6 and 4/6 and 5/6 and 6/6 of that pi. If I was to cut this calzone, the half circle, the top half, the quadrants 1 and 2, into fourths, no big deal. I could have 1/4, 2/4, 3/4, 4/4. Just trying to remind you of 1 pi is 1 pi, but it could also be 3/3, or it could be 6/6, or it could be, well, this one we were only going halfway, so 3/6. But our pi can be cut into lots of different pieces. Now I'm going to go ahead and mark the pi, 1 full pi. I'm going to mark pi over 2 because that's where complement and supplement add up to, either adding up to pi over 2 or adding up to pi. And I'm curious as to what the complement and supplement would be of something like, ooh, can I go tricky on you? You ready? I want you guys to think of 7 pi over 12. What if my calzone was cut into 12ths? Can you make an approximation? It's not a unit circle angle. It's not. Think about it. If your calzone, and if you need to, remember your calzone, 1 pi, is just a folded pizza. If your calzone was cut into 12ths, and if you were measuring from 0 up in 12ths, where would 7 pi over 12 be? Right after pi? Why right after pi over 2? Yeah, genius. I love it. Because if we're cutting into 12ths, wouldn't this guy be 6 pi over 12? So wouldn't it be just a little bit past? So if I was just a little bit past, I can go here. It's approximate, right? We can call this one 7 pi over 12, right? So this has been cut into 6s. So I could do 1, 2, 3. There we go. That'd be 6s, right? 1, 2, 3, 4, 5, 6. There we go. I could do the same thing here. I kind of have to like do one fold on one side and one fold on another side, and I have to cut those folds in half. There we go. 1, 2, 3, 4, 5, 6. Okay, so 7 pi over 12 is the one that I'm looking at, the one that I'm trying to consider. It's one calzone that's been cut into 12. 7 pi over 12 we said is 1 past the halfway mark. So guys, what would its, let's start with supplement. What would its supplement be? Supplement needs to add up to pi, right? So some of you guys already figured out there's 5 pieces missing, right? 1, 2, 3, 4, 5. So if I have 7 pi over 12, I just need 5 more to get all the way. So my, which I could make a formula for if I wanted. I could say it's going to be pi minus 7 pi over 12. And Adam got to 5 pretty quickly. I don't know if he was counting up or if he was counting backwards, but you could think about it as 12 pi over 12. All 12 pieces take away 7. How many are missing? 5 pi over 12. Or you could think about with the picture, like I have 7 pieces, how many more to get to all 12? That's the supplement. But what's the complement? Why are you asking that? Why is Kyle asking, do you have a complement? Complements add up to angles, aka like one angle, put another angle next to it. Can I put another angle get to 90? I can subtract, but I'm not subtracting on these ones. I have to add. Didn't it go past? I'm just giving you a quick heads up. Complements and supplements are only possible if your angle is below the marker point. Does that make sense, guys? Okay. I talked just a little bit ago about how some of your brains work better in degrees than radians. I'm going to try my best to retrain your brains to think in radians too. I'm going to work real hard at it over the next 3 chapters, but specifically here in chapter 4 as we're introducing. Even everything from talking about calzones, talking about slices of calzones, etc., talking about fractions and thinking in fractions. I'm going to try real hard. Flexible rulers of radiuses. But at the end of the day, some of you are like, it's going to be helpful for me to think in degrees and go to radians after I think in degrees. And to be able to do that, we have to do a dimensional analysis. Anyone who's taking chem, what's dimensional analysis? Building bridges to get rid of what you don't want. So if you have degrees, you're building a bridge to try to get to radians. You have to somehow multiply to cancel out the degrees and incorporate radians. And whenever you're building a bridge, doesn't there have to be equality in some shape or form, right? Measured in different ways, of course. 60 minutes is 1 hour, right? If you were doing a dimensional analysis with time. They're equal but measured differently. 60 is not 1, no, but 60 minutes doesn't to be 1 hour, etc., etc. We're doing the same idea just with degrees and radians. So really quickly, before we get to converting, we've talked so much about radians and what they are. Degrees, what are degrees? A tick mark on a protractor? What are degrees? A tick mark on a protractor? What else are degrees? A tick mark on a protractor? or degrees? Well, 1 degree is 1/360th of a rotation around a circle. Ugh, really? Yeah, 1 degree is 1/360th of 2 pi. What's 2 pi? Oh, no big deal. Find the radius and then make a flexible ruler and measure around. What's a degree? I don't know, 1/360th of that. That's gross. Yeah, I know. It's really nice for instrumentation, though, as far as for protractors and making angles, etc. It's really nice for instrumentation to have degrees. But the problem is it's really hard to define as far as how it actually corresponds to the circle itself without an instrument, which is why we like radians. They're more natural. Degrees are more for instruments. Radians are more for everything else. But this is really gross, right? Do we like this equality? So let's keep going. Couldn't we reduce this? Couldn't we say that 1 degree is equal to, it's 1/180th of pi? Oh, we kind of know that one already, right? 1/180th of pi. Okay, well, we kind of already know that one. And can't we, from that, can't we say that 180 degrees is pi? There's our equality statement. There's our equality statement. So converting by, multiplying by 1 creatively to cancel out units, aka, if you want to put it in Mrs. Leon terminology, building a bridge. Degrees to radians. What if I had x degrees? Good. You guys agree with Robbie that we need 180 down here? How come? We want to get rid of what we don't want, but we need the equality statement. So what's the same as 180? Pi. Wait, pi what? Just pi. Pi what? Well, technically in parentheses, we could call it radians. Radians are actually kind of an understood unit of measurement. If you're ever talking about an angle and there's not a degree mark, obviously it's radians. Oh, it's kind of an understood. Like, go to the store. Who? You. Oh. Remember understood you in subjects of sentences, etc.? Radians is kind of understood. If there's no degree mark talking about an angle, it's a radian. So couldn't I take this to go ahead and, well, hold on. That's how to build a bridge. That's how to build a bridge to get rid of degrees. How do we build a bridge to get rid of degrees? And we'll end up with radians with our final answer. How do we build a bridge to get rid of radians? What if I was to give you something like, let's just keep it with the x terminology. X radians. Maybe it's stated, maybe it's not. Maybe they just tell you it's an angle and there's no degree mark. What bridge would you build? Pi on bottom with an understood radians. And what's on top? The understood radians would cancel out. X is still there. Pi is still there. They're still important. They don't get to cancel out. The understood labels do. But you will end up with a degree. You will end up with a degree. Kiddos, at the very end of section 4.1, there are a few formulas that come up. They aren't formulas that we're necessarily going to spend a lot of time on. They're ones from geometry that if you ever were to see them, you wouldn't necessarily just have to remember them from rote memory. Not that none of you could, but you don't necessarily have to. There are a few application-y problems at the end of homework that might use some other formulas, and I want to show you what those formulas are. They're these 2 pages. They're not ones that we're really going to emphasize a lot, but I do want you to at least play with them a little bit in homework because they do show up from time to time. So the first one is arc length. Oh, hold on. For all applications, angles must be, maybe this is why I'm making you deal with it. The first step to any of these application problems is to make sure that your angles are in radians, because if they're not in radians, the physics formulas, geometric formulas don't work. You can't use degrees in these formulas. They are built on you dealing with the actual size of the circle itself in the angle measurement, not the degree measure. So in this first one, when you have this formula for arc length equals, we know r. R is radius, theta is angle. And they give us something like a circle has a radius of 4. Oh, sweet. R equals 4 inches. Dun, dun, dun. I have a place to put that, right? Right there. Find the length of the arc. Okay. Find S when theta equals, now here's the struggle. Do I want to keep it 240 degrees? No. So what am I going to have to do to solve my problem? I'm going to have to say, okay, hold on, I need my theta, but I don't want my theta to be 240, so I need to build a bridge, yeah? And what's my bridge going to be? Pi over 180. There's my pi, there's my 180. So I end up with 240 pi over 180, but come on, we can make that better, can't we? Can't we make that 24 pi over 18? Wait, we can go even better. Can't we make that? Anybody divide both sides by 6? Or I should say reduce by dividing by 6? Yeah, you could do that too. 4 times 60, 3 times 60, good. So what am I going to plug into my formula? 4 pi over 3. And then and only then will I be able to get the correct arc length by taking the radius and taking the angle measure in, radians. I can end up with 16 pi over 3, which according to the units, arc length is still a length, and if all this is in inches, then good to go. Multiplying by a radian does not mess up my units as far as inches or feet or anything like that. Kyle, go ahead. The rest of you guys get down to other 3 formulas. You might need them tonight. It's good if they're in your notes. Yeah.
I'm guessing you'd probably be killing something if you lost out the force.
Yes. Because this is a whole 4. So think, if you were to write it like a fraction, because we have to relate the two, it'd be 4 over 1. So multiplying fractions across 16 pi over 3. Yeah. So there are a few other ones. Hey, you have some Greek letters showing up too. An italics V and italics W. Oh, no, they're not a V or a W. Might want to go back and look at your Greek alphabet. But there are some other formulas. A new variable comes up, time. I think time will recognize if it comes in a problem. I think we'll recognize time if it shows up in a problem. You guys do have linear speed, angular speed, and area of a sector. What I need you to remember for every single application, for all of them, thetas must be measured in radians. So you're going to have to convert a little bit. Now you're like, oh, it'll be easy. I plug and chug to a formula. Most of them are. If any of them get tricky, we'll talk about them tomorrow. Sound good? Okay. Tonight, finish up section 4.1. See how you do. When you get to the application problems at the end, remember, angles must be in radians. You got to build a bridge first if they give it to you in degrees. And if you're stuck, go peek at some examples. Go peek at some examples and come tomorrow with questions. Get out of here, cool kids. It's chapel day. I don't know if the bell rings in 40 seconds, if it already supposedly rang, but we're okay. Let me pause the video.